Thanks for the kind invitation. The goal of our group is to build actually a clinical scanner where a human fits in, and the goal for the application is cardiac imaging. So we are not content being as fast MRI. We need to be much faster than MRI to address this application. Our original plan was to operate this scanner at 20 millitesla amplitude at 25 kilohertz. We had some reasons why we thought it could work with these parameters, but last year we heard actual PNS studies at 25 kilohertz, and it turned out, okay, these parameters are not useful for imaging in humans. As the speed is very critical for us, we did a study on volunteers where the actual nerve simulation limits are, and it turned out that for the abdomen they are at 7 millitesla and 150 kilohertz. Details will be given by Ingo Schmale later. And there's not much room to improve this, so we have to live with this and see whether the prospect of MPI to make very fast images is still valid. So we have to do, unfortunately, a little bit math to know whether this is possible or not. So how is the coding in the MPI done? It's quite simple. First, you place your field point left of the voxel. Then you have in the middle some magnetic field, and it's by definition minus XS, where XS is the field where the particles are sufficiently saturated. Then you move the field point to the right. You are here in the magnetization curve. You have a delta H, and this gives you the voxel. So you need a field change of 2xs to get the voxel. If you want to know how big the voxel actually is, you just have to divide the field step with, by the gradient, and then you end up with the size of the voxel. But for this talk here, we don't need the size. We just have to know for getting one voxel, you need a field step of 2xs. So, how big is this xs? That's actually a quite complicated question, because there are several ways to do MPI imaging. You can reconstruct, you can choose not to reconstruct, you can have very high concentrations, low concentrations, long integration time, and so on. You have various parameters in your reconstruction process. So the best thing we can do to estimate the XS we need is to look at our images and see what resolution we can get, and we see, okay, at 2.5 Tesla per meter, voxel is the reasonable size of a voxel is 1 millimeter. Below, you don't gain anything anymore with Resovist. So if we would apply 10 millitesla dry field amplitude, we would just have 8 voxels along the side of the image. So to encode 8 voxels, we need 8 information, so information up to the 8th harmonics. This is the purple dot here. And then we see we need a relative signal strength in the spectrum of Resovist of this level that it is useful for MPI imaging at reasonable physiological concentrations and high speed. In future, we can expect to have better tracer material, something that behaves like 25 to 30 nanometer Lechauvet equivalent. So we would be here, somewhere between the 20th and 30th harmonics would be useful for imaging. This would mean that in future we can expect an XS of 0.3 to 0.5. All the next estimations will be done with XS of 0.4. So then let's start to encode an MPI image. we have our drive field, some amplitude, and at first we have the first field change of 2xs, and we learned we get that voxel out of it. And then next 2xs field change, next voxel, and so on. And in the end, we have reached the amplitude, and now we can compute how many voxels we have. It's just a over 2xs. Okay, we do not stop here. We go on until we have full period reached, and we have 4 times the voxels, so 2a over xs, in the period t with a time of 1 over f. F is the frequency. Then we can just divide the two quantities and get the best possible voxel rate what we can get in the system. It's just number of voxels divided by time for the voxels, and we get 2af over xs. So let's compare what we expected in the original system and what we expect now for the voxel rate. In the original system, we expected about 2.5 million voxels per second, which is good if you compare it to MRI. It's actually much higher than practical MRI voxel scanning rates. And now, with the new limits, we get even more. So it seems that we do not have any problem, but actually that's not true, because we scanned for this estimation only along a line, and just scanning along a line doesn't give you a decent image in the end. So you have to go to 2 and eventually 3 dimensions. So what do? Again, we apply our drive field, so we get now in space, in real space, a voxel with a field change of 2xs, the next, and so on, until we have reach the highest field value, so the amplitude. Then we do a step to the right and go down again, next step to the right, and so on until we have filled at least the plane, and then we have to go into the 3rd dimension. We just focus onto one period, and what we see is that in this period we need a total field change of 4xs. So we can compute the field change we need for encoding line by line. It's just 4xs over t is 4xsf. Okay, let's compare what we originally expected and what we get now. Originally, we expected roughly 40 Tesla per second, which alone is already well beyond nerve stimulation limits, so patients will feel that. But if you fold it fast enough, you can get also below the nerve stimulation limits. So it's somewhere at the edge where imaging is feasible or not feasible. But with the new parameters, we would need a much higher field change, and therefore the scanning speed would be needed to be greatly reduced to be within the physiological limits. Okay, so that's not the way to go. Therefore, we need to introduce an additional trick. We need to encode at least one plane in a way that no nerve stimulation in the patients occur. This is done in a way that you apply not only one drive field, but in the orthogonal direction another drive field. You end up with a shoot trajectory, for example. It's the simplest case. You can end up with other trajectories if you do something more complicated. And the benefit is, at high frequencies, the patient can tolerate much higher DHDTs, so much higher changes in field. Actually, the change in drive field that we use is around 2000 Tesla per second. So, again, we can do the math. We need 2xs to encode a voxel, and now we encode the plane in some fancy manner. And it's quite easy to compute the number of voxels in one plane. Just two amplitudes multiplied and this divided by the square of xs. We have the voxel rate, so the best possible number of voxel per second that we can acquire. Just copied from the previous slides. So we can compute the time for encoding one plane. So you can't encode a plane faster than this. Slower is always possible, but not faster. So we have one plane encoded, and then we have to go into 3D. So first plane, next plane, and so on. And these planes are again separated by 2xs. This allows us to compute the focus field speed needed for plane-by-plane scanning. And this we can put into our table of what was planned and what we get now. Okay, what was planned is well below 1 Tesla per second. So absolutely no problem in terms of physiology and quite easy to implement technology-wise. But with the new parameters, we get 27 Tesla per second, which is maybe feasible, depends on how often you fold your next frequency, but it's somewhere close to nerve simulations, and the nerves are already stressed by the drive fields. So maybe that is still too high. But luckily, with the estimations, I was a little bit too optimistic up to now, because I assumed that we get voxel by voxel by voxel, and always scanning one voxel and then completely leaving it. In practice, I don't know any sequence that does this. All sequences scan voxels at least 2 times, sometimes multiple times. So the practical scanning speed is reduced. My estimation is you don't get anything better as a 50% efficiency. Probably you lay slightly below 50% scanning efficiency. And if you put that in, we see, oh, the voxel rate, factor of 2, it was high, it's still high, it's probably feasible for the application we plan. And the plane-by-plane focus field speed, what we need is, it comes to a level where it will be probably tolerable even if you go a long distance in one direction. But still, line-by-line scanning is not feasible. So it is necessary that we have this fast plane encoding to have a very high voxel rate. Okay, I did this estimations assuming the particles react like ideal Legevre particles. That may be not true, so we have to make sure that the tracer can be operated at a higher drive field frequency and a lower amplitude. For the higher drive field frequency aspect, I can refer you to my next talk on this topic. The conclusion is, yes, it works. For the low amplitude, it's just 2 additional slides to show you that it works. Here's the spectrum of residuists, first in red crosses at 7 millitesla and then in green at 21 millitesla. You can clearly see that the signal you get with a higher drive field amplitude is much higher than at the lower drive field amplitude. So at the first glance it seems, oh, we have here a big problem, but actually that's not the case, because the 21 millitesla case, you also have a larger field of view. And for example, if you encode only up to the third harmonics, you have 3 voxels along the line. And in the 7 millitesla case, the 3 voxels are much smaller than the 21 millitesla case. So we have to compare the third harmonics of the red crosses with the 9th harmonics of the green axis, and you see, okay, it seems to lie on the same level. If we do a proper scaling of the 7 millitesla data in the frequency range, you see, oh, it's quite close. Actually, lower amplitude is slightly better than higher amplitude. So probably also the tracer will work at the changed parameters. If you had looked at this problem in the perspective of X-space, then you would have thought maybe that's trivial. Okay, it seems to work in principle, but maybe the scanner becomes too difficult. Actually, that's also not the case. You cannot use the same scanner, you have to change it, but in total the complexity is not increased. For example, for the dry-field system, which is a very complex system, the complexity is actually reduced because you do not dissipate that much heat, and you do not need so many expensive capacitors. On the bad side is it's very difficult to get hold on amplifiers that operate with enough power at this frequency range. What really becomes worse is the focus field system, because we need to change the fields in a faster way than we previously thought, but I think I found a smart solution for that. And the last point is the receive amplifier. This is also critical because only a good receive amplifier gives you enough signal to noise for this application, and this becomes easier because you are far away from your 1/f noise, and the lower relative bandwidth makes matching much more easy. Not much, slightly more easy. So in conclusion, if you intended to use MPI not for the very fast scanning rates, your application will probably not affected by the change of parameters, because, okay, the tracer works, at least Reservist works, and so just stay happy, and with a good contrast agent, but still realistic contrast agent, probably also our application goal is reachable. If you would need to stick to Reservist, then things become more difficult. I don't think we get more than 300,000 voxels per second out of an MPI scanner using the performance of Reservist, which may be slightly too low for the application that we plan. And for the feed-free line scanning, okay, that's still excellent if you want to have the best signal-to-noise ratio, but it will never become as fast as a feed-free point scanner due to physiological limitations. And yes, we have to go through our design and adapt everything what we already ordered, made, and so to facilitate this new parameters. Thank you. Any questions?